Here's our first lesson for the Calculus and Vectors course. This lesson is on the derivatives of polynomial functions. Now, in your previous course, in the Advanced Functions course, you should have been introduced to the idea that to calculate an instantaneous rate of change, you can do that by finding the slope of the tangent line. So I'm going to write tangent here for our first blank at a point on the curve. So the slope of the tangent tells you the instantaneous rate of change of the function at any point on the curve. You also learned that you can determine this value by finding what's called the derivative of the function using Newton's quotient. Newton's quotient, which I have down here, and if that doesn't look familiar to you at all, make sure to click the link to the video that I'll put up at the top right now. That'll take you to an explanation of what Newton's quotient is in detail. I'll do a really quick review of it in this lesson, but I'm expecting that this is just a refresher. You already know about Newton's quotient and about limits of secant slopes and how they tell you the slope of the tangent. We're going to use Newton's quotient to find the equation of the derivative for this function. And then after we do that once, I'm going to show you the derivative rules that would allow us to find the equation of the derivative of that function without having to use Newton's quotient. But we'll practice Newton's quotient once anyway. So let me just go into Desmos, give you a really quick reminder about what Newton's quotient is doing. Alright, here's this 3x squared plus 2x plus 4 function. This function, it's curved, it's a parabola, so it doesn't have a constant rate of change. It's always changing at different rates. The equation of the derivative of this function would tell us how the function is changing at any one exact point, and that can be represented by a tangent slope. So look at this black tangent line here. The slope of that black line would tell us the instantaneous rate of change of the function at that point right there when x is 0. Now, since we only know that one point on the tangent line, it's really difficult to figure out the slope of that tangent line. So what we do is we use Newton's quotient. And what's the idea behind Newton's quotient? Well, Newton's quotient, what it does, it finds the limit of the slope of the secant lines, which I have drawn a secant line here in purple, as the change in x, which we call h, approaches 0. So I have Desmos telling me a couple values here. I have it telling me the slope of the tangent line, indicated by f prime at the a value that I've chosen. A is the x value. And it's telling me the slope of the tangent at this point is 2. The slope of that is 2. And I also have it calculating for me the slope of the purple secant line, and it's telling me that that is 6.02. Notice those two numbers are not even close right now. But as I move this point closer and closer and closer and closer along the function to this point where we want the instantaneous rate of change at, notice that the slope of the secant will approach the slope of the tangent. And that's the whole idea behind Newton's quotient. So watch as I move that point closer, pay attention to this 6 number. It's going to approach this 2 number. The slope of the secant is going to approach the slope of the tangent. So as that secant line gets smaller, as the points move closer together, the slope of the secant approaches the slope of the tangent. So that's the idea behind Newton's quotient. And we can calculate the slope of any of those secant lines we see because we know the coordinates of all the points on the parabola. So I could find the coordinates of 2 points on that secant line, and if we know 2 points on a line, we can just use our slope formula to find its slope. So let's look back at Newton's quotient formula. That's all it's saying. All it's doing is it's calculating a change in y, that's what the numerator is doing, divided by a change in x, which we call h. And it wants that change in x to approach 0. Why? Because as the change in x approaches 0, we saw that the secant slopes approach the slope of the tangent, and that's what we want. We want the slope of the tangent. That's what a derivative does. It tells you the slope of a tangent at any point we want. Okay, now that's a quick refresher on Newton's quotient. Let's use it once. So let's find the equation of the derivative of this function. So the notation for a derivative is f apostrophe x. That means the derivative of f at x. We say f prime of x equals, and then we do the limit as the change in x, which we call h, approaches 0, of f at x plus h. So this function at x plus h, so change each of the x's to x plus h, 3x plus h squared plus 2 times x plus h plus 4. And then we have to subtract the f at x function. So we subtract, and make sure you put in brackets, 3x squared plus 2x plus 4. So this is just going to find the change in the y values for us. And then in the denominator, this is all over our change in x, which we are calling h. And then we simplify this. In the numerator, we want to expand it all out, collect any like terms we have, and then something nice should happen. Now I should mention right now, this function, we can't just plug 0 in for h right now, because if we did that, we would get 0 over 0, which is undefined. That would be meaningless to us. So what we have to do is what's called remove the discontinuity by simplifying the numerator, collecting the like terms, and something nice is going to happen that will allow us to actually get a continuous function that we can sub 0 in for. So let's keep writing our limit statement, the limit as h approaches 0, and then let's expand the numerator. Now, make sure you are careful to follow the correct order of operations, and make sure you remember that x plus h squared is not just x squared plus h squared. You have to actually multiply the binomials, do x plus h times x plus h. So if we do that, I'll leave this 3 for now. If I do x plus h squared, so x plus h times itself, I would get x squared plus 2xh plus h squared. And I'll expand this 2 into here for now, why not? Actually, let me erase this and expand the 3 in at this step as well. So it would actually be 3x squared plus 6xh plus 3h squared. Okay, now I'll expand the 2 in, 2x plus 2h plus 4, and then I need to subtract all 3 of these terms. So subtract the 3x squared, subtract the 2x, and subtract the 4. And this is all over h. Let's collect all our like terms and simplify as much as we can. And watch what happens. Every term that does not have an h should cancel out. I have a 3x squared minus 3x squared. That's 0. I have a 2x minus 2x. That's 0. I have a 4 minus 4. That's 0. All I have left are 3 terms in the numerator. There, there, and there. Do you notice what's the same between all 3 terms? They all have an h. So we could common factor that h out. So f prime of x equals the limit as h approaches 0 of, let me common factor an h from the numerator, and I get 6x plus 3h plus 2. And this is all over h. Do you see what we can do now? I can't plug in 0 for h right now, because that would still give me 0 over 0. That's undefined. But I can cancel these h's as long as I know for sure I'm not canceling a 0 over 0. And the only thing I know for sure h is not is 0. H can't be 0. We're approaching 0. So that allows me to cancel these out. Anything divided by itself is 1 as long as those anythings aren't 0. And I know they're not 0 because we are approaching 0. We're not actually at 0. So I can cancel those out. And now what I have is a continuous function where the limit would be equal to the value if I actually just plugged 0 in for h. So I can just write f prime of x equals, and I don't have to write limit anymore. I can just sub 0 in for this h, and I get 6x plus 3 times 0 plus 2. So f prime of x, the equation of the derivative, is 6x plus 2. So this equation, make sure you understand what this equation tells us. This equation would tell us the slope of the tangent, aka the instantaneous rate of change, of the original function at any x value we want. Let me go back to the Desmos graph. If I wanted the instantaneous rate of change when x is 0, all I would have to do is plug 0 in for x, and it would tell it to me. 6 times 0 plus 2 is 2. And look, there's the instantaneous rate of change. It's 2. So if we want the instantaneous rate of change, let's say when x was 1, if I want the instantaneous rate of change at that point there, well, that's a steep tangent slope. The instantaneous rate of change, according to Desmos, is 8, but we can get that as well. Just plug 1 in for x. 6 times 1 plus 2 is 8. And part B actually asks us to find an instantaneous rate of change. It says calculate f prime at 5, and then interpret what does that represent. So remember, the equation of our derivative was 6x plus 2. So if we want f prime at 5, that's asking what's the instantaneous rate of change, or the slope of the tangent, at a point on the original function when x is 5. So we plug 5 into the derivative, and we get 32. And what does this represent? I've said it a few times here, but let's write this out. It tells us the instantaneous rate of change of the original function when x is 5 is 32. Graphically speaking, that would be the slope of the tangent line on the original function at the point 5, f at 5, wherever that is. And there's the graph there just to demonstrate that for you. So there's the point 5, f at 5. If I wanted the y value, just plug 5 into the original function. Tells me that point. If I want the slope of the tangent at that point, the equation of the derivative tells me that. So the slope of that blue line is equal to f prime at 5, which we figured out is 32. Now, using Newton's quotient is a little bit time consuming. But don't worry, there's a set of rules that allow us to find derivatives a lot quicker, and we're going to learn a lot of derivative rules in this unit. Let's start off with a few basic ones. And now to understand the first rule, the constant rule, keep in mind a derivative is telling you the rate of change of the original function. So if our original function is a constant, well, constants don't change, they don't have a variable with them. So what would be the rate of change? What would be the value of the derivative at any point? It would just be 0. So for example, if our original function, let's say, was f at x equals 87. Well, that function is always 87 no matter what value of x. It's never changing. So that should make sense to you why the derivative of that function would always have a value of 0 no matter what the x value is, because the original function is never changing. One we're going to focus on today is the power rule. So if we have, let me just make up a function here. Let's say we have the function f at x equals x to the power of 5. We can differentiate this function using Newton's quotient, but it's a lot quicker to use something called the power rule. And the power rule tells us if we have a power function, x to the power of some number, we can find its derivative by just taking the exponent and writing it as the coefficient. So we take this exponent n and we write it as the coefficient of the power, and then we reduce the exponent on the power by 1. So the derivative of this, f prime of x, we take the exponent 5, write it as the coefficient, we keep the base of the power as x, and then reduce its exponent by 1. So it becomes 5x to the power of 4. And that's the power rule. That's all you would have to do to find the derivative. Like I said, we could have done Newton's quotient. You would get this, but this is way quicker. And I'll show you a proof of that in just 1 second. This power rule is going to be the foundation of today's lesson. These next 3 are all very related to it. So for example, the constant multiple rule. What if our function is some constant multiple of another function? So for example, let's say our function is 4 times x to the 5. Let's say that's our function. It's 4 multiplied by that power function. How do we find its derivative? Well, it turns out we just differentiate that power, just like we did before, using the power rule, and then multiply that derivative by whatever the constant multiple is. So what I mean by that is, all we have to do is find the derivative of x to the 5 and multiply that derivative by 4. So I'll do 4 multiplied by the derivative of x to the 5. And what's the derivative of x to the 5? Well, we did that up here. It's 5x to the 4. So I do 4 times 5x to the 4. And we could simplify that, of course. F prime of x equals 4 times 5. That's 20. So 20 x to the 4. So how most people think of this, most people think you take the exponent and you multiply that by the coefficient. Find 5 times 4 is 20. That works. And then reduce the exponent by 1. That's 4. That's great. That's how we're going to think of it from here on out. But what we're actually doing is this constant multiple rule. We're finding the derivative of the power function and then multiplying that derivative by the coefficient. If we look back to that first example we did, do you see how we could have done this way quicker? Each term, oh, and maybe I should talk to you about, okay, before we go back to the first example, let me talk to you about the sum rule. If we have a function that is a sum or a difference of multiple functions, we can just differentiate each of the functions separately and add or subtract them together. So for example, if we have f at x plus g at x and we want the derivative of that function, all we have to do is find the derivative of f at x plus the derivative of g at x. So for example, let's say our original function was 5x squared plus 4x. The derivative of this, f prime of x, would be equal to, we just have to differentiate each of those functions separately. So differentiate 5x squared, bring the exponent down, multiply it by the coefficient, so 2 times 5 is 10. X to the, reduce the exponent by 1, so it becomes 1. Plus, now keep in mind on this x, there's an exponent of 1. So 1 times 4 is 4. And then we'd have x to the 0, which means there are no x's. We don't have to write it. X to the 0 is just 1. So there's our derivative. And same thing if it was minus. Let me just make one up quickly. Let's say our function was 3x cubed plus, oh, not plus, minus this time. 3x cubed minus 7. Why not? The derivative, we differentiate 3x cubed. That's 9x squared. And then we subtract the derivative. Oh, that's just a constant. The derivative of any constant is 0. So I wouldn't need to write minus 0. The derivative would just be 9x squared. So let's look back at this first example. To find the derivative of this, I would just have to differentiate each of these three terms separately using the power rule. So the derivative of 3x squared, multiply the 2 by the coefficient and get 6. Keep the x and reduce its exponent by 1, so it would just be 6x to the 1, or just 6x. Then I do plus the derivative of 2x, that has an exponent of 1, 1 times 2 is 2, x to the power of 0, which means there is no x, and then plus the derivative of a constant. Derivative of any constant is 0, so I wouldn't have to write that either. 6x plus 2 is the equation of the derivative. And look, that's what we got using Newton's quotient. So the derivative rules make it a lot quicker. So I showed you this. Now, like I said, the most important thing we've learned here is the power rule. There is a proof as to why we are allowed to do this. And I'll put a link at the top right now if you want to watch the full proof of that power rule. I encourage you to watch it. I'm not going to require you to do this, or I'm not going to test you on this proof, because it does involve something called the binomial theorem, which you may never have seen before. If you've taken the data management course, you've definitely seen it. But if you haven't, you probably have not seen the binomial theorem before. It has to do with expanding binomials, and you probably learned in grade 11 how to use Pascal's triangle to do that. Binomial theorem is related to that. But regardless, it's a good idea to watch the proof just to know that it comes from somewhere. We're not just making up this power rule. Alright, let's do a few examples now. Let's find the equation of the derivative of a few different functions. Let's start off with f at x equals 3x to the power of 5. We want the derivative, f prime of x, would equal, take the exponent on the x, multiply it by the coefficient, 3 times 5 is 15, keep the x, and reduce its exponent by 1. So it becomes 15x to the 4. Part B, it's a constant. F at x is always 71, which means it's never changing, which means its derivative is 0. C, do you remember a square root symbol is actually an exponent? I could rewrite the original function as x to the 1 over 2, and now I can just use my power rule. F prime of x, the derivative of x to the half, would equal, bring the exponent down as the coefficient, keep the base of the power as x, and then reduce the exponent by 1. A half minus 1, that's negative a half. And then if you have a power with a negative exponent, you shouldn't leave that in the final answer. You should rewrite this as its reciprocal with a positive exponent. Or, another way of thinking of that, just move that power to the denominator and it changes the sign of its exponent. So f prime of x equals 1 over 2x to the half. I would accept that as a final answer, but typically if we have an x to the half, you would rewrite that as root x, just as it was in the original question. There we go. We've done 3 derivatives. Keep in mind, these are equations that would tell you the instantaneous rate of change of the original functions at any value of x we want. 3 more. Cubed root of x. Well, let me rewrite that. It is the same thing, equivalent to x to the power of a third. Now we can find the derivative. And when it's written, the function is written in terms of y, we could just write y prime, that's fine. Or we could use something called Leibniz notation. We could write this as dy over dx. Both of those mean the derivative of y with respect to x. Doesn't matter which one we use. Let's use dy over dx. We haven't done that before. Dy over dx equals, bring the 1/3 down as the coefficient, keep the x, reduce the exponent by 1. A third minus 1, so a third minus 3/3 is negative 2/3. Negative 2/3. So since there's a negative exponent, we have to take this power of x, move it to the denominator. So dy over dx equals 1 over 3 times x to the power of positive 2/3. Or cubed root of x squared, however you would want to write it. I'll leave it like that for now. That's fine. Part E, we have 1 over x. Well, let me rewrite that. This x, if we brought it back up to the numerator, it would change the sign of its exponent from 1 to negative 1, and that'll make our differentiation quite a bit easier. Y equals x to the negative 1. This is equivalent to the line above. And now I can use the power rule to differentiate this. I'll write y prime this time. This means the same thing as dy over dx. So the derivative of the function equals, bring the exponent down as the coefficient, keep the x as the base of the power, and reduce the exponent by 1. So negative 1 take away 1 is negative 2. And then we need to express our final answer with no negative exponents. So I would take that power, the x to the negative 2 power, and move it to the denominator. That'll change the sign of its exponent. Negative 1 over x squared. Part F. Since our variable is in the denominator again, it's going to be useful if we bring that up to the numerator so that we can use our power rule. Now there is a way to use something called quotient rule of derivatives, but we don't know that yet, so we'll do this one by bringing up that power to the numerator. So the original function is equal to negative 1 x to the negative 5. So I just rewrote the original function. Now let me find its derivative. Let me do dy over dx again. Equals, multiply the exponent by the coefficient. Negative 1 times negative 5 is 5. Keep the x, reduce its exponent by 1. Now take that power and move it to the denominator, and that changes the sign of its exponent. We have 5 over x to the 6. So we've done 6 derivatives now. All of them involve power rule. Let's do some where we'll need to use the sum and difference rule of derivatives as well. It's as simple as just differentiating all the terms separately and adding or subtracting them together. So for part A, y prime equals, let's differentiate 5x to the 6. 6 times 5 is 30. X to the reduce the exponent by 1. Now let's differentiate this term. 3 times negative 4 is negative 12. X squared. And now let's differentiate this term. The derivative of any constant is 0, so we could, I suppose, write plus 0, but we don't need to write that. Part B. We're back to function notation, so I'll write f prime of x for the derivative. Actually, before I find the derivative, let me rewrite the original function, f at x, changing that square root symbol to an exponent. So f at x equals negative 3x to the 5 plus 8x to the power of 1 over 2 minus 9.3. Now I'll find the derivative. F prime of x equals 5 times negative 3 is negative 15, x to the 4, plus, find the derivative of this 8x to the half, so do a half times 8, which is 4. X to the a half minus 1 is negative a half. And then minus the derivative of 9.3, which is 0, so I don't have to write it. Let's just rewrite this derivative so that it doesn't have a negative exponent by moving the power to the denominator. So negative 15x to the 4 plus 4 over x to the power of positive a half, or just root x. Two more examples. Now part C is a product of two functions, so we will learn something called the product rule later. But for now, in order to differentiate this, you would have to rewrite the original function in standard form, meaning expand it out. So let's multiply it out. 2x squared plus 2x minus 3x minus 3. And then we'll collect any like terms that we have. So this g at x function equals 2x squared minus x minus 3. And now we can differentiate this. Now it's just three terms being subtracted. We can use our power rule and our difference rule, and we can find the derivative. So the derivative of the first term would be 4x to the power of 1. The derivative of the second term, keep in mind there's an exponent of 1 here. So 1 times negative 1 is negative 1. And then keep the x, reduce its exponent by 1, so it becomes x to the 0. And x to the 0 is just 1, so we can erase that. Minus the derivative of 3, which is 0, so we don't need that. So there's our derivative, 4x minus 1. Part D. There's a few ways we could do this. There is something called the quotient rule, which we'll learn later. But for now, I think it's easier if we just simplify it and then differentiate. So for example, both of these terms in the numerator are being divided by that 4x to the 5. Let me write this as two separate fractions. So I have negative 8x to the 6 that is being divided by 4x to the 5. Plus, I also have the 8x squared, which is being divided by the 4x to the 5. Now let me simplify. I've got negative 8 divided by 4, that's negative 2. X to the 6 divided by x to the 5. When dividing powers with the same base, you keep the base and subtract the exponents. 6 minus 5 is 1. Plus, 8 divided by 4 is 2. X squared divided by x to the 5. Keep the base, subtract the exponents, I get negative 3. Now this looks like something I could differentiate using the power rule. So h prime of x would equal negative 2 x to the 0. I multiplied the 1 times the negative 2, and I reduced the exponent by 1. So x to the 0 means there are no x's. And then the second term, when I differentiate that term, negative 3 times 2 is negative 6. X to the, decrease the exponent by 1, it becomes negative 4. So the equation of the derivative equals negative 2 minus 6 over x to the 4. The last two examples we're going to do here are going to make sure you fully understand what these derivative equations that we're coming up with, what they actually are and what they do. So let's look at example 3. It says determine an equation for the tangent to the curve, and it gives us a curve, and it tells us where we want the tangent line at. We want it at an x value of negative 1. So we want the equation of the tangent line at that point. So our end goal is to come up with the equation of a tangent line. Well, the equation of any line is y equals mx plus b, where we need the slope and the y-intercept. So using calculus, we can figure this out. Let me go over to Desmos and just show you exactly what we're looking for. Okay, here's that curve that it gave us, the f at x function. That's our red function here. The question says we want the equation of the tangent line to that function at an x value of negative 1. So let me just zoom in a little bit here. Here's the function when x is negative 1. It's at negative 1, negative 6. If I were to draw a tangent line to that function at that point, that would be a line that just touches it at that one point. So it would be this green line here. We want the equation of that line. And to find the equation of that line, we need the slope and the y-intercept. Well, the slope of the line, that's what the derivative tells us. So the derivative would tell us the slope of that tangent. If we plugged negative 1 into that derivative, it would tell us the slope of the tangent at an x value of negative 1. So I have Desmos doing that for me here. It says, hey, the slope It's 6. The slope of this green line is 6. We're also going to need to know the y-intercept of the line. Well, I see right here the y-intercept is 0, but how are we going to figure that out? Well, if we know the slope of a line, and we know a point on the line, this point -1, -6, I know it's on the tangent line. And how would we get the -6 value? How do we get the y value? Since we don't have the equation of the tangent line yet, well, we have the equation of the red function. It's the original equation, the f of x equation. If I were to plug -1 into that original function, it would tell me where the red function is when x is -1. And that's exactly where the tangent line is going to be there as well, because by definition, a tangent line will touch the original function at that point. So let's follow along with how we are going to figure out that slope 6 and the y-intercept 0 algebraically without having Desmos do it for us. So since I want the slope and the y-intercept, I'm going to need two things. I'm going to need a point on the tangent line that will give me xy, and I'm going to need the slope of the tangent line that will give me m, and then I can use that information to solve for b, and then I could write the equation. So to find a point on the tangent line, well, I know the tangent line touches that function at that point. So the tangent line and the function are at the same point when x is -1. So if I want a point on the tangent line shares a point with the original function when x is -1. So just plug -1 into the original function, and then that not only tells us where the original function is when x is -1, but it also tells us where the tangent line would be when x is -1 as well. So we'll plug -1 into the original function, 4 times -1 cubed, plus 3 times -1 squared, minus 5. If we simplify this, I get -1 cubed is -1, so 4 times -1 is -4. -1 squared is 1, so plus 3 times 1, minus 5. This gives me -6. So I have the point -1, -6 is where the tangent line touches the original function. Let's look back at Desmos. Notice, yes, that is the point, -1, -6. That's where the tangent line touches the original function. So we have a point on the tangent line. This is our xy point. To write the equation of the tangent line, I need its slope as well. That's exactly what a derivative gives us. It gives us the slope of the tangent at any point we want. So I'll need to find the equation of the derivative. So I'll need f prime of x. So let's differentiate this original function. Differentiate the first term, I would get 3 times 4 is 12, x squared. 2 times 3 is 6, x to the 1, minus the derivative of 5 is 0. So there's my derivative. I want the slope of the tangent line when x is -1, so plug -1 into the equation of the derivative, and it'll give us the slope of that tangent line. 12 times -1 squared plus 6 times -1. That's just 12 minus 6, which is 6. So we figured out the slope is 6. So we have slope, we have a point. We could use that information to write the equation of the tangent line by solving for b. So let's plug in our y value, x value, and m value into this y equals mx plus b equation. -6 equals 6 times -1 plus b. And then if I solve this, I have -6 equals -6 plus b. What can I add to -6 to get -6? 0. So my b value is 0. So I can now write the equation of the tangent line. Y equals, plug in your m value, your slope, plus my b value of 0. So y equals 6x is the equation of that tangent line. The equation of this green line, y equals 6x. Let me add a y equals 6x function, and notice it goes right over top of the green one. We found the correct equation of the tangent line. Last example, example 4. Determine the point, or points, on the graph of y equals x squared times x plus 3, where the slope of the tangent is 24. So this time it tells us the slope of the tangent, and it says, hey, where on the original function is the slope of the tangent 24? Let's look at this in Desmos so you understand, and then we'll go back and do it algebraically. Okay, the red function is that original function, the x squared times x plus 3. We're interested in where is the slope of the tangent, 24. Remember, the equation of the derivative tells us the slope of the tangent, and I have Desmos finding the slope of the tangent for us right here. We want to know, when is that 24? So where is that 24? Well, I think I see it would be 24. Oh, I found a spot right there. The slope of that green line is 24. That tangent line is 24. It happens right there when x is 2. Any other places? It looks like it would happen again right there when x is -4. So how are we going to find those algebraically? Well, the derivative tells us the slope of the tangent. So if we set the derivative equal to 24, we should then be able to solve for x and get those two values. So let's try that out. Oh, and it wants the points, not just the x values. So I would also need the y coordinate that goes with the x value of -4, and the y coordinate that goes with the x value of 2. So I'll have to get those as well. And I'll get those by plugging the x values into the original function, because the tangent line touches the original function at those points. I'm going to need to find the derivative of this function. Right now it's a product of two things, and I don't want to do product rule, so I'm going to start by expanding out the original function. X squared times x is x cubed, and x squared times 3 is 3x squared. Now let me differentiate this. Y prime equals 3x squared plus 6x. Now I know this equation tells me the slope of the tangent at any point I want, and I'm interested in, when is the slope of the tangent 24? So let me set this equation equal to 24 and solve it. 24 equals 3x squared plus 6x. This is a quadratic to solve, so I will set it to 0 to solve. 3x squared plus 6x minus 24. Now I can solve this by factoring or quadratic formula. Factoring is definitely going to be quicker, especially if I take out a common factor first. So divide each of the terms by 3. And now that quadratic in the brackets would factor to x plus 4 times x minus 2, because those numbers satisfy the product and sum. And now this product of three things would be 0 if either x plus 4 was 0, or if x minus 2 was 0. So if x was -4, or if x was 2. So I know the two places, the two x values, where the slope of the tangent would be 24. The question wants the points. Anytime it specifically asks you for the points, we also need the y values of the points. So I have the x values, I need the y values as well. So plug those x values into the original function. So I'll figure out f at -4 and f at 2 as well. So we would just sub those into the original function. If I plug -4 in, that would give me 16 times -1, that's -16. If I plugged 2 in, 2 squared is 4 times 5, it would give me 20. So my points, where the slope of the tangent is 24, would be the points -4, -16, and 2, 20. And if we look back at our Desmos graph, 220, yes, the slope of the tangent is 24. And where was it? -4. There we go, -4, -16. The slope of the tangent is also 24. So we found them. That's the end of the first lesson. Make sure you try out the practice questions that go along with this, because we're going to keep building off of these rules really quickly in the beginning of this course. So make sure you get good at the power rule and you have a good understanding of what an equation of derivative tells you about a function.